In this video, we're going to take a look at an application related to electronics, and this is an example of what we call Kirchhoff's voltage law. And so when we're talking about a simple circuit, we can have something like a battery attached to a light bulb, which is a form of a resistor. And what happens is in the circuit, so imagine that you have some sort of battery here. So I'll just try to draw a battery. And so inside of this circuit, we have some sort of maybe light bulb. So here's my beautiful drawing of a light bulb. So there's a light bulb. And what we do is we connect the terminals of the battery so that when we attach both terminals to this light bulb, that the light bulb lights up. And so it reduces, or it emits heat. The light bulb gets hot, as you probably realize. There's always a little bit of a heat associated with that. And that is where we get what's called a voltage drop. Okay, so when the current passes through a resistor, such as a light bulb or motor, some of the voltage is used up, so to speak. By Ohm's law, this voltage drop across a resistor is given by V equals Ri. So if this had something like, maybe 0.1 amps of current, just as an example, and this had a resistance of 100 ohms, we write like that, the omega, then the voltage drop across this light bulb would be V equals Ri. Well, the resistance is 100 ohms multiplied by the current traveling through that circuit. So we would have, we would require a 10 volt drop across the light bulb. Now, this is not necessarily, these values are not necessarily realistic. I'm just trying to give the example of how this would work. Now, a lot of times circuits get more complex, where maybe we have multiple batteries. So these guys are batteries. This is a 30 volt, a 20 volt, a 40 volt, and a 10 volt battery, or some sort of voltage source. And then we have these guys here, which are the resistors. And so those could be light bulbs, those could be other devices. We usually draw resistors. It's kind of this generic component. And so to figure out, what we want to do is we want to know how much current is, what I1, I2, I3, and I4. So I is the current, R is the resistance, and then V is the voltage. So to figure out how much current is flowing through all of these subcircuits, we use Kirchhoff's voltage law. And it says that the algebraic sum of the Ri voltage drops, so Ri is simply using Ohm's law, so the voltage drop across a device is the product of resistance and current, that the voltage drop in one direction around a loop equals the algebraic sum of the voltage sources in the same direction around the loop. So to give you a better example, sometimes reading this doesn't help us out too much, but what we're going to first study is just this first loop right here. Now we see that there's I1 current, and that's what we want to figure out. We want to solve for I1, but we see that the voltage drop across these three resistors is going to be 1 times I1, so it's resistance times current, plus 2 times I1, and that's the voltage drop across this resistor, plus 3 times I1, and that gives us 6 times I1, just within that loop. But what we also have to consider is that there's also current flowing in the opposite direction in this loop too. So this resistor right here actually has another voltage drop associated with it, and that is due to this current here. And so this resistor in terms of I2 would be 1 times I2. But it's in the opposite direction. So this is where electronics can be kind of a little bit different. But since this current is traveling clockwise and this current is traveling clockwise, current flows this way via I1, but via I2 it flows back this way because of how we see the current flowing inside of this second loop. So the way we're going to combine these is we're going to say, well, we have 6I1 voltage drop in the first circuit, and then we have minus the 1 times I2. And that's going to equal the total voltage in loop number 1. So we have to consider all of the voltage drops within that loop, and we also have to consider the negative of the voltage drop across that resistor due to I2. So this is one of our equations, and this is really our equation for that first loop. Let's move on down to the second loop. So in the second loop, we have 3 resistors, and that's going to be 4I2 plus 4I2 plus 1I2, and so that's going to give us a total of 9I2. And this is all going to equal the 20 volts for that particular loop. Okay, but let's think about all of the other currents that are flowing, are kind of intersecting with this branch right here and this branch right here. So right here we have the current flowing I1, and so the voltage drop across this guy is going to be 1I1, but it's in the negative direction. It's in the direction opposite to where I2 is flowing. I2 is flowing counterclockwise. I1 is flowing counterclockwise, but they sort of are going in opposite directions, as we've denoted here with the arrows. So basically, if you want to kind of shortcut rules to solving these things, then the only positive term that you're going to have in there is the total voltage drop across that individual loop. And then also this resistor here, right? This resistor here is receiving current from I3, and so the voltage drop because of this third loop is going to be 4I3, but that's going to be negative, since, once again, I3 is flowing in the opposite direction as I2. So you can see that the negative terms, here we only have 1 because there's only a loop below loop number 1, but for the second loop, we have to consider the current from the first loop and the current in the third loop. Okay, let's see if we can get the hang of this thing. So in the third loop, we are going to have 2I3 plus 1I3 plus 4I3. That's going to give us 7I3. That's positive because that's just for that one loop. But then we see that I2 also flows through this resistor here, and so that's going to be minus 4 times I2. And we also have current I4 flowing through a part of the branch, one of the branches that's inside of loop 3, and that's going to be 2 times I4, but it's going to be negative because it's flowing, again, in the opposite direction through that resistor than is I3. And those are going to sum up to give us 40 volts. And now we can move on to the fourth loop. Well, how many currents current drops or voltage drops are there going to be? Well, there's going to be one due to the loop itself, which will be 3I4 plus 2I4 plus 2I4, which gives us 7I4. But then we also have I3, again, flowing in the opposite direction because I4 is going this way, but I3 is going the opposite way. And so we are going to have negative 2I3. And those have to equal the total voltage source in that loop, which is 10. So now we have our four equations in 4 variables. We're going to attempt to solve this. We've got to do a little bit of rearranging here. So in my augmented matrix, what I do know is these are going to be 30, 20, 40, and 10. It doesn't matter what order you insert the equations into your matrix, because remember, one of the things that happens with Gaussian elimination is rows can be swapped. So the order in which you populate these 4 equations into the matrix is not important, as long as you don't put 30 in the first component, but then put 6i minus 1i2 in like the 4th component. Okay, so I have to make sure that these are I1, I2, I3, and I4, and then my constants over on the right. So this has 6I1 minus 1I2, 0I3, 0I4. The second equation has negative 1I1 plus 9I2 minus 4i3, 0i4 equals 20. And in the third loop, I have 0i1, I have negative 4i2, 7i3, negative 2i4 equals 40. And in the fourth equation, we have 0i1, 0i2, negative 2i3, 7i4. And those are going to give us our four equations. And so now, not by hand, but using technology, we're going to compute the row-reduced form of this system of equations. Our reduced form comes out to this, which right away I see leading ones in each column, for each column within each row. And so I know that I'm going to have a unique solution in this case. So I1, I2, I3, I4, written in vector form, is going to be 6.36, 8.14, 11.73, and 4.78. So these are typically going to be measures in amps or amperes. So we can say there are 6.36 amps flowing through through loop 1, 8.14 amps through loop 2, and so on and so forth. So this is really just an application where we're using some sort of scientific law. If you didn't really understand reading this, don't worry too much about it as long as you're able to follow how we built that circuit. If there were more of these, we would just kind of keep repeating Kirchhoff's voltage law for each of those subcircuits, or each of those loops.